Now we will see the how we can find the position of or the location of Vmax and the V minimum on the transmission line using the Smith chart. So here the total voltage is given by this expression. Here total voltage is this is the incident voltage at z equals to 0, and you can write in term of reflection coefficient. Similarly, the total current is given by this expression. These are the two expressions for total voltage and total current. That is, if you have a transmission line somehow here, at a particular value of that, you can find the what is the total voltage and total current. That is the total incident voltage and the reflected voltage. Now the impedance at this location Z just is given by, well, that is the line impedance V over I, and this is the expression in terms of the reflection coefficient. Now the maximum voltage here will occur. We have already seen in the previous lectures that it will be occur when this has the phase is 0. So when this total phase here around is 0, then in that case this will become 1 plus magnitude of gamma L, and this have the magnitude 1, you will get this one V maximum, and this will occur when this total phase is 0. Similarly, at this location where this phase become at the value of Z, at this location where this phase becomes 0, the voltage is maximum, while at the same position the current will be minimum, and current is given by here. So when you put this one to be 0, this will become 1 minus gamma L. So at the same location the voltage will be maximum, and the current at that same point the current will be minimum. Here there's a current is there. The voltage and current are opposite. Here the current will be maximum minimum and the voltage maximum. Similarly, the voltage will have the minimum magnitude when this phase is pi or minus pi. In that case, you will get the minus sign here. So this voltage will be minimum. So minimum voltage will be there, is given by this expression. Here minus sign is there. However, this will occur when this total phase is pi or minus pi. And at the same position of the transmission line, you will get the maximum current, which is now 1 plus, because it is already minus, it will become plus. So what you can see here, if you have a transmission line, Smith chart, let me draw some Smith chart here, small Smith chart. So, or you can go back. So, some so let's take anyone here. For example, this is the case. So what it means that when you move on the line, let draw me here. You have a Smith chart here. So when particular value of Z, you have initial value of theta phase. So you may find the here. So this is tau, sorry, gamma L. And when you add some transmission line position, you have to move in the, so if your transmission line and you will have some load here, so this will give you some gamma L. You can plot it here on the gamma complex plane, and then you move in particular direction, the Z direction, then your phase will change. Your phase will change. So you will reach here somehow for different value of Z, you will get the another value. So this will be maximum when this phase is 0. It means you are reaching at this location. So this is, what is this one? This is the total reflection coefficient at a given point. So this part is actually a gamma, which is equals to, we already have seen, this is how we can write j 2 pi z plus theta. So this part is actually a reflection coefficient at a location given by z. So this V will be maximum when this reflection coefficient have the 0 phase or the values are real. Positive real. So we will get the positive real values when this is 0 phase. So you will have. So here you will be there. So it means though when you will move in the transmission line and where you will get the 0 phase, it means you are reaching at this point. So the location uh, will be here when this phi is 0. So this is the length. You will find this angle you are moving, or you can say you move around this distance in the z this direction, so that you get phase. So for example, this is lambda by, for example, it comes out to be lambda by 10. So you are moving lambda by 10 here to reach at this point. So if you see the Smith chart, so this lambda you find, it means you are moving lambda by 10 here, and you will get the maximum voltage. So the maximum voltage will occur on this line. But you have to find, okay, what is the initial reflection coefficient at the load and how much lambda you have to move to reach at this point. So you will get the distance at a distance. What is the, and always the maximum will occur when this gamma will come to the positive real axis of this plane. Similarly, for the minimum voltage, this phase has to be minus pi. So what you have to move in a such a way, and you will reach on this line. So when you reach on this point, so this will become the phase which have the pi phase. This is the pi or minus pi. So here you will get here. So on this positive real axis, you will get the maximum voltage location, and the negative real axis, you will get the minimum voltage location. And to find the distance of the transmission line, you have to find this length in lambda for the maximum voltage location, and this length here for the minimum voltage location. So what it means that the Vmax or Vmax is located where the gamma is real and positive on positive x gamma axis. Similarly, Vm or Imax is located where the gamma is real and negative on the negative gamma axis. Okay, so this is what it mean. And same thing where you have the voltage maximum, so here the current will be minimum at this point and this location. So, and here you have the magnitude of this one. So whatever magnitude you have rotate this one, and you will reach. It means if you move along the constant magnitude line and reach here, you will get the location of the V maximum. See, or you can say when you move along the constant SWR, because this is also a constant SWR circle. So constant SWR circle will give you the location of Vmax or Vmin when which cut in the positive real axis and the negative real axis. Now in that case, the line impedance, are we saying the Z in? So because sometimes we call to be because we are seeing here at this point. So this is the line impedance, or sometimes if we terminated, if we are this section is cut here, so we can say this is the input impedance here. So this will be the maximum because V max upon I minimum, because at the same location voltage maximum, current is minimum. So you will get the Z in maximum here as that is the input impedance where the max voltage is maximum. We are finding the input impedance or the line impedance where the voltage is maximum. That's mean here. So when you find out V max over I minimum at this location where you have the maximum voltage, so V max over V minimum will be comes out to be, this will be cancelled out, and here 1 plus gamma over 1 minus magnitude gamma will be the S. This will be S into Z naught. Or simply if you normalize this, you divide by Z naught. So you will get the normalized input impedance at the location of where you are getting the maximum voltage is simply the S. So if you find the S, if you find the standing wave ratio, directly that will give you the input impedance on this point location. So what it means that because S is real, so this will become a real. So this will become a resistive load. So where you have the peak voltages or maxima occurs, there the load will become the real. The load will become the real here. Because on this line, the load will be always be real. This is a resistive line. So here the reactive component of the load is always zero. So this is the point here that at the point of maximum voltage, you will have the resistive load. Similarly, at the point where the voltage is minimum, so voltage is minimum. So in that case, you have the this you have Z naught over S. So you divide V minima over I max, and you will get the that, and you normalize it, you will get 1 over S. So this is also a real quantity, and this value 1 by S. So you will here. So this is also a resistive load. So in that case, where you have the maximum voltage or minimum voltage, you will get the line impedance at those locations to be the resistive in nature. So here what we have written, the line impedance at a position of V max is purely resistive. SWR can be used to find the Z in at maximum location or Z in at the minimum location. So you can use the Smith chart to find the location of V max and V minimum. So here is given here in chart. So this is a gamma plane. So this is a real axis. So on this location, so here you will get the V maximum. V maximum. So and here this is the line. If you this one. So if you draw this one, so this is the negative real axis. So on this line, whenever the gamma you find, it means here if you find the gamma to be at this location, it means you are having the minimum voltage. If the gamma lies on this line at this location or at this point or at this point, you will get the maximum voltage at this one. So to find the location, what you do, you just find the load impedance uh, and then you find the reflection coefficient and then you rotate in a such a way that you will cut here when you reach here. So this lambda towards you are hanging toward generator. So when you find this length, you take the difference and find the lambda, how much lambda you have moved from into here. This is the distance from the load which will at which you will have the maximum voltage. Similarly, if you further move and you reach here, then you will get the where the minimum will occur. This lambda will give you the minimum, and this distance is lambda by 4. We already know total this circle length has circumference has a lambda by 2 distance will cover to get the 360-degree phase. So here this is 180-degree phase. So by lambda by 4 moving from a length, so you will reach the minimum. So if you can find this one, so definitely you just add lambda by 4 to get the minimum. So here what we have written, the voltage Vmax occurs where Z and max is located on the chart, and that is on the positive this axis, and that's called the point of open circuit line. This is here we are moving the point of open circuit. So this will be the point of open circuit will have the infinite impedance here at this point because of open circuit, and this is the point where you have the short circuit. So notice that Vmax and Vminimum are lambda by 4 apart. So you can see this one. So this you can use a position. Next, you can also directly find the normalized admittance. So if you have the line impedance given, so you can just read that line impedance on the Smith chart, and using that Smith chart, you can find the admittance. One way is to just do the invert. You use the formula. This is a mathematical way. If you know the line impedance, this is a normalized line impedance or any impedance which is normalized. You just take invert, you will get a normalized by impedance. Now, how without doing this analysis, you can directly use on the Smith chart. So what you do here? So if you know this one normalized Z, so you can find its equivalents this sigma and its magnitude in phase. So you, for example, you get here, this is the this equivalent gamma and this is the phase here phi. So this will have some here. So you can have a relation here. Z is given by 1 plus gamma, 1 minus gamma, and where this is a magnitude and phase. Now to take the admittance here, what you do? You invert the Z, you will get this one. Now to have a minus here, just what you have to change this phase. You you just change minus to positive. So just using this expression, the gamma is given by here. Now this gamma is not of y. This gamma is related to z. So you have z dash have the this gamma. Equivalent of this normalized impedance have the gamma. So we are talking of the gamma right now. You have magnitude and phase, and here your phase. Now what do you do? Just you multiply this. What is mean by minus? Minus is just a e to the minus j pi. When you open it, you will get the minus sign here. So it means this phase will be um, added for here. When you multiply two complex number, then the phase will be added and the magnitude will be multiplied. It has a one magnitude and the phase is j pi. So what it means that phase will be, because it's a minus, so it is a minus. The phase will be subtracted. And here also you will have the minus sign and the phase will be subtracted. So this is a relation. If you see simply add, if you have any complex number, any impedance, you can find by using this. So it means this is the, you can assume that this is a some sort of impedance. Like this is called as Z1 dash. This is Z. So this is some impedance whose value is given by this one, whose reflection coefficient is given by this expression here. So this is a e to the power j gamma tau minus pi. So this is a new complex number which have this one. So and what do you know? And this value are same. This value are this exactly same because this is equal to z dash. So it means the admittance of this one is same as the the this impedance, new impedance whose gamma is given by this expression. And how to find this one? If you know already this gamma, so here the magnitude are same, the phase are different. If you move this theta by pi, you will reach this impedance. So what it means that if you, this is a minus sign, so you are decreasing the phase. So you are moving in the clockwise. So what you do, you just move here by pi. Pi means you have to 180 degree. So if you move 180 degree, this angle, so now this phase will be, you will reach here. So if this is phi, then this will be 5 minus pi here. So what do you have a straight line and you will reach. So if this is gamma, then have the phase phi. So this is the reflection coefficient whose magnitude is same, but the phase is now phi minus phi. This this one, if it is 5 gamma, this will be phi gamma minus phi. So just by rotating by 180 degree, so when you reach and you find this complex number using the Smith chart, so this complex number actually are admittance of this one. So this is the, just you can read the complex number and that complex number will be the admittance. Similarly, if you know the admittance, you back convert now because when you move reverse, then you have to add the pi. So you move by 180 degree and you will get the next complex number which will be the inverse of this one. So these two relation will be inverse. If you move on this 180 degree, these the complex numbers are invert to each other. This will be, so if this is admittance, this will become uh, the impedance. If this is impedance, this will become the admittance, and so on. So by just, it's easier in the Smith chart by rotating by 180 degree or lambda by 4 wavelength, you will get the admittance. So this is how it says here. The admittance is equal to the impedance obtained using the reflection coefficient phase shifted by 180 degree or lambda by 4. So you can directly find out the admittance here. So here we have a problem to understand how we can find this one. So this is for you to do it. This I will give you some hint here. So what is a problem is 30 meter long lossless. So here the length is 30 meters. So you are taking the transmission line whose load is connected with the load here ZL. So load is connected here somehow, and this length is 30 meter. So you are here, and this is 30-meter length here. Now the line with Z naught is 50 ohm operating at 2. So Z naught is given. Sometimes they write only 50 ohm line. In some problem they will write say 50 ohm transmission line. So transmission line. So it means here if they are giving this value, it means the Z naught is 50 ohm. So here they are directly given the Z naught. So the characteristic impedance is 50 ohm. This is a standard value. Some transmission line I have 75 ohm and so on. So 50, 75 ohm are the standard value. Generally they are used practically. So if it is 50 ohm line and this is real, it means you have it is lossless or distortionless. So here they given the lossless transmission line. And the frequency of operation is 2 megahertz. So f is given. So if f is given, you can find the lambda. It means lambda is given for you, and uh, here for lambda you have, if f is given and you want to find the lambda, you also need to know the value of velocity. So you have to know the velocity, and they already given the velocity of the Propagation of wave in the transmission line is 0.6 of the speed of light. So you can find the lambda here. The reflection coefficient. So now you will first directly use the formula. You can use the formula, and then you can also use a Smith chart. So you have to use it both way. The reflection coefficient you can find using the formula. So here it will be what is ZL minus Z naught over ZL plus Z naught. So you can find the reflection coefficient, and because this is load is complex now and Z naught is real, so this will comes out to be complex. So complex, then you will find its magnitude and phase. You will get them. Then ascending wave ratios, you just use this one to find this, and you can find the input impedance using the previous formulas. Now using the Smith chart, what you will do? So Smith chart, what you will do? You first you have the Z naught. So using the Smith chart, you can download the Smith chart on from the internet, or I will also upload on the course material. So using the Smith chart, you find the this is so here ZL is 60 plus J40. Now first of all you divide with the 50 ohm line to normalize this. So you divide 50 ohm and you divide here 50 ohm, and then this is the value of R. So you find the R circle. For example, you are getting R circle here. So this is a some R circle you find out whose value is given by 60 over 50. Now next, this is the X part. You this is 4 upon 5. So you find 4 upon 5 somehow. This is positive, for example. So you will upper part with there. So somehow the arc is going some like this. So let this is the 40 over 50 ratio. So this is the intersection. So when you have this point, now you use the scale to find this distance. So you know that this length is 1. If you have a unit circle here, this magnitude is 1, and this point will be the your gamma L. So you using the protractor, you can measure this ratio, this length over this length, you can find this one. So because you have, for example, this is a O point, and this is a P point, and this is the let S point. So just what is OS is 1 and OP is gamma L. So what we have, you measure OS or OP with your scale over OS will give you what is OP. OP is same ratio will be same. So divide by the 1. So due to this, if a Smith chart have the different scale, using this concept you will get the same result, because if it is somehow scaled down or zoom out, then still you can use the same relation to get the scale. But somehow this is zoomed down, or this is scaled to the half. In this case, if you use your normal scale, you will have different values. So how to get the exact? You have to find the relative. If this is 1, so what is the this value with respect to this one? You will get the exact one. So using relation, you can find this gamma L. You measure OP with the scale and OS, and you use the expression. And you can find the phase by extending this one. You can read that value. So you can find phase. Then extending ratios. You make this circle. You make this circle, and where it cuts, you find the R circle which is passing through this point, and this value of R will be the equals to S. For example, it comes out to be 2, for example. So then this is a here we have the two values, so it will be the 2 SWR2. Then input impedance, how to find input impedance? So if you this is the Z gamma L location and 30-meter length, so you find 30-meter in terms of lambda. You know what is the lambda, and then move in the, because you are moving towards the generator side, you move clockwise until you get some finally you get this position here you get. So now this will be the gamma in, and you, because magnitude remains same, just you extend here and you measure this angle. um, you extend here, so this angle will be the gamma phi in. It will be a negative here. If you find out like this, it will be a positive. Both will be same. This is how you can proceed. This is another problem. Here you can go further and do it yourself, and you can find the location. So you will see these questions from the book, uh, from Saduko, and they are solved examples. You can go through them yourself. So here, for problem one, here you can use this also, figure to do it. So what I have done, that they have find the ZL. ZL is 1.2 and zero point 0.06. So their R circle is zero point 0.2 and you have the zero point 0.8. So what you have to do, let me enlarge this one. So if you enlarge here, because they are positive, so we are focusing on the upper side. So here, what they have the circle was, you was having the 1.2 and 0 0.8. 1.2 you find here. So here you have 1.2. This is 1.2, 1.4, 1.6, and so on. This is 2. The 1.2. So you are moving. This is the R circle here. Next, you have what is this will be the zero point 0.8. So here you see the what is the zero point 0.8. You can see from here. This is 1.4, 1.3, 1.2, 1.1, the 1, zero point 0.9. Sorry, zero point 0.8 will be there. So you can see here. So this is 1. So we have to find out this one. So here it is 0 point 0.8. So finally what you are getting, they are the point. The intersection of these two, they have find the P. So this is the gamma L for this one load. And they extend here, then they read this angle, this total angle they have. This is the angle here. They have read this one, and this is the magnitude. Now using this formula, the OP over OQ is 3.2 they have measured, and this is 9.1, which is equal to 0.35. So there, and then to find this length, so they have they find the reflection coefficient at the load, and then you can use to find the input impedance by rotating from this point the term of lambda and reaching here. So, and so you can do it yourself. So we have completed the Smith chart, and we have seen here what is the fundamental Smith chart, what is the basic concept behind it, and how we can use to find out the different values of uh, this the reflection coefficient and the impedance, admittance, location of Vmax, Vmin, SWR, and the parameters. So Smith chart is frequently used in the industry, and now because in modern days we have very high and computation facilities are there. So you can also do the same thing using the formulas, using the programs, but still it is used, and it is generally used in the load matching. You have if you have a transmission line which is mismatched towards the load. So in general, we have to match the load to the transmission line. So there it is very useful. So you can use the Smith chart, and here you can find what should be the load or what should be the section of a transmission line you can connect with what type of stub you may use to match the load. Okay, so I stop it here. Or you can see the reference also here. So these are the references which I have gone through while making these slides. So you can also go through this references.